more energy demanding. What is the term state of this situation now? Right? S1, WS. Oh, that means this WS1R state might be somewhere out here. And which corresponds to the removal of one of the inner electrons. And what will this fellow do for me? He will give this much of kinetic energy. So which means when I do the experiment, there might be another peak out here. And what does that peak most likely do to the WS 1/2 state with a lot less kinetic energy, because it takes a lot more energy to remove the electron, and what is left behind is only a small part of it, which is important to the electron as it is leaving as kinetic energy. So when I do a photoelectron experiment with a photon that is reasonably energetic, what am I actually doing? I can remove one electron here, I can remove another one here. If I have enough energy, I can probably remove even this one. And what will that be? A WP again. But then the WP is sitting up there somewhere. And much less kinetic energy than what you get from these states. In other words, I can actually map out the entire orbital diagram for this molecule or the atom. And that's the power of the photoelectron experiment. Of course, I'm not going to bother you with theorems like Koopman's theorem and all that, but I'm just mentioning this Koopman's theorem. I won't ask you in the exam. And there's a little theorem, which is the whole basis for it, which says, if I can calculate the orbital energy for all these guys, the negative of that is what I see in my experiment. Because at the end of the day, the energy of this orbital is what is reflected off the tape. Don't bother about these theorems. I'm just throwing it at you because if somebody in a seminar talks about Koopman's theorem, you know he's talking about a photoelectron experiment. And that's all I want you to keep in mind. But what I really want you to really pick up is the fact that you can actually remove electron from here, get a photoelectron spectrum. I can remove it from here, get a photoelectron spectrum. Remove it from here, and so on. And therefore, when I do a photoelectron experiment, I will actually get the picture of every orbital that you can possibly remove. But that will depend on what photon energy you have used. Generally, when you use UV visible light, generally UV is used, and sometimes deep UV. When I say deep UV, I'm talking of the light of the energy of about 15 eV, 10 eV, 8 eV, and so on. It's pretty large. And that's called UV-based photoelectron spectroscopy. And sometimes people even call it as, of course, only nowadays people have started using, when I say nowadays, the last 20 years, visible light is used because you have lasers, very powerful lasers, and visible light is used in some very devious manner to do photoelectron experiments. So the conventional photoelectron experiment is basically used in the UV mode. The UV has a lot of energy, and therefore if I use a UV photon, I can actually remove quite a few electrons and get my entire spectrum, which tells me about each of these orbitals. And therefore it's called UV-CES, ultraviolet photoelectron spectroscopy. But then with UV you can only do so much. You can probably remove maybe this, and maybe this. But to remove all these which are sitting right inside the core and really held by the nucleus very strongly, well, you can't do it with UV. They need much more. And when I say much more, what is the next on your electromagnetic spectrum after UV? What? CES, and that's X-ray photoelectron spectroscopy. You shine X-rays on that, and X-rays are enormously energetic. And when you shine X-rays, you can keep out these guys, and then you can have all these electrons come out, and therefore you can start looking at the structure or the energy level diagram for the core electrons. So you can therefore see this as a very powerful technique really. You can use UV light, look at maybe the valence electrons, and maybe a little bit inside. But if I want to look at the core electrons, then I need to take X-rays and shine X-rays on them, and then do X-ray photoelectron spectroscopy, in which case I'm looking at electrons buried deep inside the core of the orbital structure. You can do either of these. But depending on what you do, You are either a UV photoelectron spectroscopist or an XPS spectroscopist, or sometimes even called XPS. X-ray photoelectron spectroscopy. These are little jargons that people use, but they all mean the same thing. The point is, I can either use UV vis, and there are standard sources you can take. You know, you can take a helium discharge tube, and you will get energies like 40 eV or 23 eV, which you can use. They're all in UV region. But then, if you want to use X-rays, you take out to a few, maybe a few axion theories, and then you can start digging out the core electrons. You get structure or the orbital structural information, the orbital energy information for the core electrons. This is what you would do if you're doing for atoms. You do the same thing for molecules. But in molecules, what are you doing? You're not removing from atomic orbitals, you're removing from molecular orbitals. And we have seen how you construct molecular orbitals, right? Using 1s sigma, 2s sigma, and it goes on. So let's say if I have what do we get? 1s sigma, 1s sigma star, 2s, 2s, sigma, 2s sigma star, and then 2p, 2p pi, 2p sigma, 2p sigma star, and 2p pi star. Okay, you know this. Now, supposing I gave you, let's say, boron, B2. How many electrons does B2 have? 10 electrons. Okay, so if I have 10 electrons, it's 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Now, if I do a photoelectron experiment on this, which is the first electron I'm going to remove? I'll remove this guys. And therefore, we haven't learned yet, and maybe by the end of today we will start looking at that. When I remove this is the electronic configuration. Just like for an electronic configuration, you have an atomic term state. For this electronic configuration, you will have a molecular term state. So I start from a term state of the molecule, and I will end up at a term state for the ion. And I will get exactly the same situation. I have a photoelectron spectrum, which essentially gives me the energy of these orbitals. If my energy is good enough, what do? I can remove from here. I can remove from here. But if I want to remove these, what do? Go to XPS. Again, if I'm getting very close to the nucleus and I have to remove electrons from deep into the core, then I have to take recourse to X-ray photoelectron spectroscopy. The point, therefore, is using UV vis or UV photons, I can look at maybe this structure. And using X-ray photoelectron spectroscopy, I can probably look at the structure exactly the same way that you did for molecules, atoms. Yeah.
Maybe I'm not understanding how you want to how can we judge, okay, when we are putting X-ray lights over there, why not only the valence electrons will go off and moreover if the inner electrons are going, how can we know that okay the inner electrons have already been?
Yeah. When I'm doing X-ray photoelectron, these electrons will be pulled out. But of course, the energy that I am now giving for the molecule will be enough to remove these also. So I will get this and this when I do X-ray photoelectron. So I will be removing an electron from here, I'll get a peak for that. I can remove an electron from here, get a peak for that. Electron from here, one peak for that. One peak for that. In other words, I will get the photoelectron peaks which correspond not only to the valence electrons but will also correspond to the inner electrons and the core electrons. But when I do UV photoelectron spectroscopy, I might remove these and then I run out of energy. The photon is not capable of removing any of these because the energy isn't good enough. So then your question might be, why not just do X-ray all the time? Why do you do even photoelectron spectroscopy with UV light? Well, experimentally that is a lot easier. And therefore, and today with lasers, it becomes extremely easy to be able to do experiments on the UV photoelectron spectrum. The problem is, if I use X-rays and I remove this electron, what's going to be the kinetic energy of that guy? oh, it goes screaming out. You know, it's got huge kinetic energy, so it goes screaming out. And then I have a problem with resolution. Because by the time I wake up, the electron is already there. You know, there's very short time intervals, and therefore experimentally it becomes a bit of a problem getting resolution under such experiments. That's the reason why we don't want to look at these with X-ray photoelectron spectroscopy, because they have too much kinetic energy. Of course, you can then say, maybe I'll put some grids and slow them down. You complicate life for yourself. UV photoelectron spectroscopy is great for all this. And X-ray photoelectron spectroscopy is great for looking at the core electrons, where you really need that amount of energy to be able to yank that electron out from where it is sitting. Because it is sitting very close to the nucleus, and therefore it's very tightly bound. You need a lot of energy, which is what the X-ray photons will give you. So the experiment therefore is conducted either as UVPES, ultraviolet photoelectron, or as X-ray photoelectron. Little later I will, just for the heck of it, tell you some of the interesting things and complications that come about when you do X-ray photoelectron. Not there for the exam, I'm just going to tell you that. What I'm telling you now is something I will test you in the exam. But when I get to that part where there are some very interesting complications, I will let you know what they are. And I also let you know that you don't have to worry about that as far as the examination is concerned. The reason I keep saying all this is the moment I say it's not for the exam, I think you'll listen better. I know, I believe that the examination is a big interference to education. But unfortunately, the system doesn't have any other method. That's the reason we have to set up an exam for you. Okay, now let's see how we can do this experiment for a molecule. When you do it for a molecule, we go back to potential curves, right? We are used to thinking about molecules in terms of potential things. So here's the ground state of, let's say, oxygen. Or let's take boron. I think we wrote this for boron, right? 1, 2, 3, 4, 5, 6, 7, 8. It's a boron. Let me make it simpler for you. It's here, beryllium. Beryllium is what? 4 electrons, right? So this must be the electronic configuration for beryllium 2. Well, beryllium 2 won't exist, so let me make it simpler. Perhaps go here. One, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14. So this must be nitrogen. Right? That's the electronic configuration for nitrogen. For that configuration, what do you think? It's all completely filled out. Everything is filled, isn't it? This is filled, this is filled, this is filled. Everything is filled. If everything is filled, what should it look like? In an atom we saw, if everything is filled, what's your term state? Singlet S. So it should be something like that. No orbital angular momentum, no spin angular momentum. Everything is paired. Everything is simple. And let us say the potential curve for nitrogen is like this. Now what do I do when I do a photoelectron experiment? Let me say I do a UV photoelectron experiment. When I do a UV photoelectron experiment, what electron am I going to be knocking out? That's going to be the easiest. This one, right? Of course, in the case of oxygen and nitrogen, when I remove this, so this is going to be 2p pi 4 and 2p sigma 2. When I knock off one electron from here, what am I going to get there? 2p pi 4, 2p sigma 1. And there must be a potential curve corresponding to that, right? This is N2 plus. There must be a potential curve corresponding to this. And what do you think will happen to that potential curve? Will it be shifted one side or other side? Yeah, I removed a bonding electron, right? You recall all the things I told you. I remove a bonding electron. What happens to the molecule? The molecule just becomes a little weaker. I removed it. Therefore, that potential curve cannot lie exactly on top. Where will the potential curve lie? Slightly on this side. So this must be the internuclear distance for nitrogen, and this must be the internuclear distance for N2 plus. So when I'm going from here and I'm removing an electron, what happens? actually making a transition from here to here. Very similar to what you saw in absorption spectroscopy. We said we draw potential curves and we make molecules jump from one level to the other. And what are they doing under those circumstances? They are just shifting orbitals. Here they are not shifting orbitals. One of them is gone completely. Doesn't matter. I'm still dealing with a potential curve to a potential curve like transition. So I'm going from a completely filled orbital to one in which I have one electron less in the sigma orbital. Bonding has been merged. The potential curve shifts. Doesn't matter. It's the same thing as saying I'm going from this level to this level in a photoelectronic experiment. And the curve shifts this way. What do you get? If the curves are one on top of the other, what will I get? Progression or a sequence? Sequence. When the curve shifts, what will I get? I'll get a progression. Same thing. Whatever you learned earlier will hold over here. So now, if I go from here, so I'll see a progression on here. So when I do a photoelectron experiment under these circumstances, what am I seeing really? I am leaving the ion in this vibration state, in this vibration state, in this vibration state, and so on. And therefore my photoelectron experiment will look like something like this. While here, I was actually probing the two J states, the two spin orbit states. In a molecular photoelectron spectroscopy, what am I really probing? I am probing the various vibration levels in the excited state. If I leave the molecule in this vibration state, what will be the kinetic energy of the electron? The largest or the smallest? Let's say the proton is this much. This is the kinetic energy. If I leave the molecule in this vibration state, what is the kinetic energy of the